Look inside a major hospital floor, a web of randomized intersecting paths. Now, look at a modern automobile assembly line, strictly gated, sequential, and synchronized. Operations management treats layout as a strategic variable, the precise arrangement of resources and tasks designed to control flow. Designing a layout requires two active decisions: determining exactly where your transforming resources, like machinery and staff, are physically positioned, and then precisely allocating specific work elements to those spaces. Together, these spatial decisions govern the flow of your transformed resources, like raw materials in a factory, information processed in an office, or customers navigating a facility. The engineering challenge is to arrange massive, multi-million-dollar assets in a way that systematically minimizes friction, reduces holding costs, and eliminates wait times. You either mathematically design the flow of an operation, or the physical constraints of the space will define your output. This is the volume variety matrix, the framework engineers use to translate business demand into physical space. It plots how output quantity, volume on the x-axis, interacts with the range of customized offerings, variety on the y-axis. Depending on where a business falls on this curve, it maps to one of four specific layout zones, transitioning from highly flexible to rigid and linear. Violating the mathematical gravity of this matrix, for example, using a high-volume layout for a high-variety product, guarantees operational breakdown. At the top left of the matrix is Zone 1, the fixed position layout. This is used when the transformed resource is too massive, heavy, or delicate to move. Because the target is stationary, the spatial challenge reverses. All the transforming resources, the cranes, the concrete, and the specialized tradesmen, must dynamically flow to the site of the product. Moving down the curve brings us to Zone 2, the functional layout. This applies to medium volume operations, where similar processes or machines are grouped together into specialized departments. In a job shop or a medical facility, patients or products move intermittently in batches between these specialized zones, based on their unique processing requirements. To optimize this, engineers use a flow matrix. It multiplies the interdepartmental load, the number of movements per day, by the cost to travel that distance, identifying the adjacencies that minimize total travel. While this setup offers the flexibility to handle varied demands, the spatial math creates friction. Products wait in queues between departments, creating expensive work-in-progress bottlenecks. Next, Zone 3 introduces the cell layout. This is a hybrid structure designed to extract product line efficiency out of functional flexibility. This binary component machine matrix is the first step in production flow analysis. It maps components directly to machines. The algorithm iteratively rearranges the data to identify families of products with similar steps, sorting them into localized blocks. By physically grouping dedicated machines into these precise clusters, each cell acts like a self-contained mini-factory. This reduces interdepartmental travel times and clears out standing inventory. Cells trade absolute functional flexibility for localized throughput. This structure also grants staff a sense of team ownership over an entire family of products. At the bottom right of the matrix sits Zone 4, the product layout. Here, transforming resources are arranged in strict sequential order according to the steps needed for production. This creates a continuous, unbroken line of identical transformed resources, typical of mass manufacturing or high-speed bottling operations. The optimization challenge here is line balancing. The required market output rate dictates a strict cycle time, the maximum allowable time frame for each sequential workstation to complete its task. This chart shows work content across 4 stages. Unequal distribution means idle time at faster stations creates a penalty, balancing loss. Engineers use precedence diagrams to sequence dependencies, rearranging work to eliminate idle time and align every station to the exact cycle time. Within product layouts, designers face a choice between a long, thin process and a short, fat process. A long, thin process breaks the work into many rapid, highly specialized stages. A short, fat process compresses the line into fewer, longer stages, capable of parallel processing and flexibility. A long, thin line maximizes theoretical efficiency through specialization, but it is brittle. A breakdown at any single node immediately halts the entire multi-million-dollar operation. Even a mathematically optimal layout fails if the external environment cannot support it. In regions like Southern Africa, specific infrastructure limitations, such as unpredictable power grids and load shedding, act as hard constraints on peak efficiency. In an environment prone to single-point power failures, a tightly coupled long-thin product layout becomes a liability. Regional engineers adapt to these physics. Operations frequently revert to robust functional layouts, or they build in manual redundancies to leverage available unskilled labor pools. These physical constraints act as mathematical weights. Managers purposefully sacrifice peak theoretical efficiency to ensure operational survival and supply chain resilience. Curious, what happens to the mathematics of layout when the transformed resource is no longer a physical object, but invisible data? Consider the Future Progress Bank case study. Historically, processing mortgage applications meant routing physical paperwork through manual validation steps. That physical paper forced the bank into a high-friction functional layout, complete with interdepartmental transport times and physical storage requirements. Digitizing the application data allowed the bank to instantly convert its operation into a high-speed product layout, eliminating physical transportation and manual data entry. This shift reduces the physical footprint, lead times, and variable costs, but it introduces a new risk profile, trading physical bottlenecks for digital vulnerabilities, like cybersecurity threats and total system downtime. Whether the work involves raw steel on a factory floor or data packets on a server, the layout serves as the logic determining how resources flow or where they fail.